Good afternoon. On behalf of the WM Keck Institute for Space Studies, or KISS as we call it, I would like to welcome you to today's event. My name is George Dragowski. I'm a professor of astronomy and a member of the KISS steering committee, and standing here for Professor Tom Prince, the director of the Institute. And we are very indebted to Caltech Space Innovation Fund and WM Keck Foundation, without whose support this would not be possible. So this Keck Institute for Space Studies is really a joint think and do tank between Caltech campus and JPL. And it's focused on ways to revolutionize space exploration, which of course builds on great successes that JPL and Caltech has had in this field in the past, and as well as robotic exploration of the solar system and so on. It is a small but very powerful and influential institute. It's been recognized internationally as one of the top think tanks in the United States. These lectures, this lecture series is really designed for the KISS affiliates, who are a small group of graduate students and postdocs. They're nominated by the faculty, and they interact with leaders in space exploration, learn about current missions and future ones, just like the one you'll hear about today. But thanks to the Zoom, we can now reach many more people, and many more people can benefit from it. So at this point, I'd like to introduce Michael O'Connell, who is a third-year graduate student in GALCIT, the aerospace department here at Caltech. He studies at the intersection of engineering and control design, machine learning, to understand how to safely apply analysis of classical techniques in modern computing methods. And he hopes that together these fields will accelerate the process for new space vehicles and push limits of autonomous robotics operating in space and other extreme environments. Mike has been a KISS affiliate since 2018, and he's currently the KISS affiliated liaison. And through that, he has met many of the leading scientists and engineers advancing space exploration. Mike also learned his BS in aerospace engineering from University of Illinois in Urbana-Champaign, and his master's in space engineering at Caltech, and is currently working towards his PhD in space engineering. So Mike, over to you.
Thank you, George. And it's great to see such a large turnout for this exciting lecture. I think that we would be a little tight in our usual lecture hall on campus in Lee's Kubota. So tonight's speaker is Dr. Bethany Ellman, who is a professor of planetary science at Caltech and is also a research scientist at NASA's Jet Propulsion Laboratories here in Pasadena. In Dr. Ellman's research, she focuses on unraveling Mars's environmental history and understanding the history of water in the solar system. She studies this through the investigation of planetary surface processes, infrared spectroscopy, and the chemical weathering and hydrothermal alteration of the planet, and also through the development of new planetary science instrumentation. Dr. Ellman stands out in her field as a leader. She is the PI of the Lunar Trailblazer, which we'll hear about tonight. And she is a member of the science teams for the Mars Exploration Rover Spirit and Opportunity, the CRISM Imaging Spectrometer on the Mars Reconnaissance Orbiter, the Mars Science Laboratory Curiosity Rover, and the Mars 2020 Perseverance Rover. In addition, she is also on the Dawn Orbiter team, which is exploring the largest asteroid and dwarf planet series, the Emmett Space Station-based imaging spectrometer to explore dust source regions, and she's working on mission concept proposals for Europa, Venus, Mars, Mars moons, asteroids, and Earth. The last thing that I'll mention today, but certainly not the least thing in our long list of achievements and contributions to the field, is that Dr. Ellman is a board member for the Planetary Society. So now I would like to welcome Dr. Bethany Ellman to tell us about the Lunar Trailblazer.
Okay, thank you so much for that intro, Michael, and I appreciate that. So we did a little tech testing before this talk started, and we found out there's a little bit of a lag, so I'm going to be asking Gina Marie at Caltech has a better internet connection and will be graciously advancing my slides. So welcome, everyone, and I'm excited to tell you about the mission that I'm the principal investigator for, which is Lunar Trailblazer. And we are a pioneering small satellite mission that's designed to answer questions about lunar water and lunar geology. I'm going to be talking to you today about, really the work over the last couple of years that's due to the people listed on this slide and many more, and the organizations involved. You'll see them on the bottom of the slide. If we go to the next slide, what I'm going to be telling you, I'm going to be telling you 3 stories today. The first story is about water on the moon, predictions and surprises, the current state of the science about what we know on water on the moon. Then I'm going to talk to you a little bit about small satellites and how this is an exciting new way to explore the solar system. And then I'm going to tell you specifically about Lunar Trailblazer and our mission, Caltech-led, to go to the moon. If we keep going here, this story, I love telling it to Caltech audiences because this is a story of water on the moon that really, when you trace back the scientific history, has deep roots at Caltech. If we go to the next slide, note that this paper was written in the early 1960s, date up there at the top corner of the screen, and it was by Ken Watson, who is doing his PhD in geological and planetary sciences with Bruce Murray and Harrison Brown in our division. And such luminaries as Urey, Harold Urey, famous geochemist, were quoted as saying he originally thought there might be water on the moon, but then concluded it was unlikely to exist for a long period of time. But as you'll see, our fearless Caltech crew argued in this 1961 paper that we wish to say that water is initially more stable on the lunar surface. Okay, so this is the start of the argument and the questions about water on the moon. If we go to the next slide, what I'm showing you here is a plane map of the moon. So you're looking from north, south, equator in the middle. And what you're seeing is the temperature as a function of time over all longitudes. So we've just spread the globe out. And what you're seeing animated is the thermal wave of the temperature change on the moon as it rotates. Now, some of you might know that the moon always keeps the same face to Earth, and because it takes 28 days to go around, that means a day on the moon is 28 Earth days. So it's kind of a long day, right? I mean, if you think your day was long, go to the moon. So what you're seeing here, though, is the huge temperature range on the moon and also the extreme temperatures on the moon. So next time you look up on the moon, you should know that you are looking at a surface that is over 400 degrees Kelvin or over 260 degrees Fahrenheit. Okay, so the surface of the moon that you're looking at, the sunlit surface, that kind of eye, dark red eye, is hot. And so this is why it was not predicted that there should be any water, ice, or any kind of water on the moon. On the other hand, you can see that when the temperature drops on the moon, it also drops quite low, right? Minus 200 and something Fahrenheit. And this is because there's no insulating blanket of an atmosphere to modulate these temperature changes. If Earth had no water and no atmosphere, it would be similarly very hot and very cold. So this is the extreme moon. If we go to the next slide, and if we turn our attention now to the poles of the moon, there's a very special environment, and this is what Watson and our Caltech crew were describing for why there might actually be water on the moon. Okay, so some of you might recall the Earth is tilted at like 23 1/3 degrees, rotates around. But like in winter, the North and the South Pole in their respective winters don't get a lot of sun, and that's because the pole is facing away from the sun. Okay, the moon does not have an extreme tilt. I've put a little doodle here of what the magnitude of the tilt is of the moon, and it's only like a little more than 1 degree on its axis. So that basically means the moon is like rotating straight up and down. Now, okay, so think about what that means for sunlight hitting or not hitting the poles. And imagine there's like a mountain or a crater and the shadow that would be cast. Okay, so if you can get that picture in your head, what I'm showing here on this figure is a topographic map of the moon. So red is high, blue is low. The lowest lows are in impact craters. And what you see colored black is a portion of the lunar surface that never sees direct sunlight. It's one of these permanently shadowed regions. And if you see PSR sprinkled somewhere in my slides, it is one of these permanently shadowed regions on the moon that never sees a single ray directly from the sun. And as you might imagine, against the cold blackness of space, these regions are cold. How cold? Well, if we go to the next slide, we have actually been able to measure now with an mission and the Lunar Reconnaissance Orbiter and a mission called Diviner, we've been able to measure just how cold those shadowed regions on the lunar pole are. And so you can see I have the temperature scale here, and those polar regions are down in the blues and the purples of the scale. It is quite cold, down in the coldest part of the moon, down to minus 400 degrees Fahrenheit in the coldest of the cold shadowed regions. How cold is this? Well, if we go to the next slide, so I've kind of blown up the bottom of the temperature scale, and what you see here are some of the ices that they're listing. And I've also just made a little doodle to see that you have the right picture in your head of ice. This is carbon dioxide ice, dry ice. You've probably played with this at some point or another, right? So this is dry ice subliming that is going directly from solid to vapor. So space is a vacuum. Any ice just sitting on the surface, unless it's very, very cold, with some temperature, you're losing some of those water molecules to vapor, and it's going to sublime. But if you get very, very cold, like 100 Kelvin cold, as on this temperature scale here, you can keep those volatiles from turning into gases over more than 1 billion years. And so what this temperature scale is showing is that when you hit 100 Kelvin, water ice is stable. And when you get even colder, to the coldest parts of the moon, other volatiles like CO2 ices, hydrogen sulfide, other things might be stable there too in these what are called cold traps. So this was Watson's essential idea, is that sustained over time, there could be in these very cold regions water ice. Now, if we go to the next slide, in the late 2000s, 2010s, that's when we started to be able to follow up on this hypothesis and like figure it out. So there were a couple of instruments that came. So what I'm showing you here in panel A is the predicted, how far would you have to dig beneath the lunar surface to find a point where water ice might be stable? And the answer was, in a few craters, there should be ice like right at the surface, or within the upper couple centimeters. Okay, and so then the question, was it there? So one thing we sent is a neutron spectrometer. That's this lens detected hydrogen, a lunar neutron detector. And anywhere that there's blue is meant to evoke water ice. So where there's a blue patch, that means there's more hydrogen. Where there's more hydrogen, there might be more H2O. Okay, that's pretty cool. So in one of those hydrogen patches then, it was followed up in 2009, the L-Cross mission, which crashed into one of these hydrogen patches to see what it would find. And if we go to the next slide, it found, in fact, so how this mission worked was it was a spacecraft that basically sent a projectile to the moon and followed that projectile down and then looked at the plume of what came off. And so with the L-Cross impactor, what we saw in those data on the L-Cross impactor slide was the fingerprints of water ice in the spectrum. So what's exciting is we were able to trace the fingerprints of water in this spectrum. So going back now to the slide that shows the two maps, the state of the science circa 2009, we had one data point where we saw in the plume of this impact something like 5% water ice. Okay, so that was great. Meanwhile, if we go to slide 12, which is about Mercury, meanwhile, elsewhere in the solar system, the Messenger spacecraft was exploring Mercury. And what it found through a whole combination of instruments, including some help from radar back on Earth, was that Mercury, some of you, Mercury, closest planet to the sun, also very hot surface during the day. Likewise, it goes up and down. So meanwhile, on Mercury, the messenger spacecraft, with some help from radar, was mapping the polar regions and found these particular regions that were in permanent shadows. They also were very cold. They had deposits that were very bright in radar, which is an indication of water ice. And then the laser altimeter also saw that these were dark, but the neutron spectrometer saw hydrogen and another instrument saw carbon. So what we found in the poles of Mercury was pretty cool. It was this layer of like fine organic carbon, and underneath it a thick set of water ice in the poles of Mercury. Okay, so to summarize, by approximately 2010, 2012-ish, we had just discovered large deposits of water ice in the poles of airless bodies whose surface temperatures elsewhere regularly got above boiling. Okay, so this was cool, and it's kind of opening up this whole new field of water on airless bodies in the solar system. Then, if we go to the next slide, back to the moon. So there was a spacecraft that went to the moon, and now we're going to delve into a little bit of technical detail, but I think you'll be able to follow the thread of the story here. So there is a spacecraft that went to the moon called Chandrayaan. It was launched by the Indian Space Agency, actually, and it carried an instrument from NASA, the Moon Mineralogy Mapper, or M-Cubed. The M-Cubed instrument was an imaging spectrometer, so it could both take pictures of the surface, and then for a given pixel, it could look at the spectrum or the fingerprint of light to see what it was made of. So what this plot is showing here on the upper left is the wavelength of light versus the amount of the reflected light. So this is a spectrum of the surface. And the reason that this type of spectrum is so important is what's going on in terms of the variability on the moon. You see that downturn coming in at 3 micrometers. That actually was very unexpected and is important. And the reason it's important is the plot that's shown over there to the right. That's because the material that causes this downturn at 3 micrometers is water. So if we go to forms of water and their fingerprints, what we see here is a zoom in now on that slide that I was showing, where you have the reflected light and then you have this absorption coming in. So when I'm talking about water on the moon, I'm actually talking about a few different things. But one of the big open science questions is figuring out which kind of water is where, because they all have this downturn at 3 micrometers, but you can tell it's at a subtly different wavelength. So there are basically 3 types of water. One is what I started talking about, water ice on the moon. That is H2O ice, kind of like the ice cubes you get out of your freezer. The other is H2O molecules that are bound to the surface. So think of a little V-shaped H2O molecule bouncing around onto the surface, maybe coming and going with temperature. Maybe when it's cold, it's bound to the surface. And when it warms up, it turns into the tracest trace of vapor, water vapor. Okay, and then the third type is water that is much harder to get out. And in fact, it's not quite water, it's OH. It's the hydroxyl, the OH, bound to a mineral. So think of an H stuck on an oxygen in a mineral. It also creates this absorption feature, although you can see they're at different spots. So if we go back one slide, backwards to the slide that is talking about water on the moon, what we see is that, so there's this downturn in the M-Cubed data, but we don't actually have the resolution or the full breadth of this absorption to map out that it's there. Something that was done was, it turns out that when spacecraft go anywhere else in the solar system, they usually zip by the Earth-Moon system and take some data. And so this is actually from this lower panel is from the Cassini spacecraft that went to Saturn. And they had snapped some data of the moon. No one really did too much of anything with it. That wasn't the point of the Cassini mission. But then when M-Cubed made its discovery of what appeared to be water on the moon, Roger Clark went back and he dug the Cassini data out of the archive because it covered further into that wavelength region, enough to see that, yes, indeed, there is this absorption feature that indicates some form of water, even in the hot, you know, up to 200, 400 degree Fahrenheit surface of the sunlit moon. Okay, so if we go forward again to the slide, this time that says time variable sunlit water. So this is forward in the correct order. Thank you. So now yet another spacecraft went mining into their archives. This was the Deep Impact mission who crashed into a comet. This spacecraft looked back and said, oh, you know, we took some measurements of the moon too, and we took them at different times of day. And looky here, that if we look at the data in the evening or the morning, it looks like there's more water in the cooler morning and the cooler evening than there is at noon in the hot surface of the moon. So maybe some of this lunar water is changing. Okay, this was like very strange, but all of us scientists are like, well, great, this is quite the mystery, and we're eager to find out what is this water and what is it doing. So if we continue forward now, the final piece of this puzzle was that also there appear to be certain rock formations. So there's a slide, localized water anomalies. Localized water anomalies, what does that mean? That means there are rocks in certain places on the moon that have enhanced water. In this case, the central portions of impact craters, which have excavated material from deep in the moon. And there were also certain types of volcanic rocks, if there are any geologists on the line, some of the more silica-rich lithologies and some of the glassy pyroclastic deposits from volcanoes are some of the things that were carrying this water signature, which was very unexpected. And so if we go to the final slide for this portion of the talk, in essence, we have a new field. And if any of you are on the line are artists, please get in touch with me because we need a doodle for this new field. You may recall, you know, in science, elementary school science class, you know, Earth has a water cycle, right? It cycles between liquid, solid at the poles, gas, it rains. What we are discovering here, and we're just starting to piece together, and I just have a bunch of boxes because there's no great picture of it yet, is we're discovering that there is, in fact, a lunar water cycle where volcanic eruptions from the mantle appear to create rocks and presumably some volcanic gases too that release water. There are also impacts coming in from comets and asteroids, some of which are icy. There's also H. H is the big mystery from the solar wind that comes in. The sun emits particles in addition to light, so H from the solar wind. And then all of this somehow goes back and forth between ice in the shadowed regions and whatever this stuff is, H2O molecules hopping around on the sunlit side of the region. And so we're trying to figure out what is the lunar water cycle. So this is kind of the state of the mystery right now. Now, if we continue forward in the talk and go forward, the next section, I'm going to take a bit of an excursion because this is where we sat at the moment we, as a team, conceived Lunar Trailblazer. So part 2 is about a parallel track. Not about science, not about lunar exploration, but about technology and what we are innovating here on Earth. And that's small satellites. So small sats, CubeSats, you may or may not have heard about this, but what this is a picture of is this is a picture of Mars from the Marco CubeSats that were traveled under their own power to Mars, took data during the InSight landing site, and you can see how big they are because that is them in the corner there on the lower left being assembled in the laboratory. So a cereal box-sized spacecraft can now travel to Mars under its own power. Small sats are super cool. So if we go to the next slide, I'm just showing you, some of the family portrait of small satellites in our CubeSat and SmallSat revolution. So these started as literally CubeSats that were 10 centimeters on a side, and they were designed to help aerospace engineering classes go through the process of spacecraft design. And then they were standardized so they could be packed in little canisters and launched as demos when launches had a little extra mass to allocate to a university to let them do this learning tool. So they started as these little cubes, but then people realized actually this is a really good idea, that if we make satellites standard sizes, we can get them access to space just riding along in the extra mass. It's kind of like an Uber pool or a Lyft pool, right? Like you might be going somewhere, but if you take a pool and jump in the car with someone else who has some extra seats, you can get there cheaper. And it's the same with getting to space. So from CubeSats to the 6-unit cereal box-sized spacecraft that go to Mars or go to Earth orbit like Asteria and hunt exoplanets, to larger payloads like what's being shown here inside a 4-meter fairing of a rocket, where there are actually 3 spacecraft kind of around a ring with a much larger primary payload on top. All kinds are getting this ride-along access. If we go to the next slide, we are in the middle of this kind of huge growth phase, and it's really mostly driven by Earth industry rather than NASA space exploration, but they kind of go hand in hand with the pushes that NASA requires feeding into new technologies for Earth and vice versa. So these standardized forms that let them slot in and take advantage of this market inefficiency of extra mass going to space, the fact that components are getting smaller and more reliable, the fact that there are new commercial players, we're effectively sort of democratizing access to space with small, capable satellites that launch for a much cheaper price because they're often riding along. And you can see in the graphic I'm showing here, this is the actual and then future projections of this aspect of spacecraft. If we go to the next slide, scientists realized the potential of this in the early 2010s, and this was a National Academy of Sciences study about the potential of the science of these small satellites. If we go to the next slide, one of the key aspects is that small is not necessarily quite so small. I mean, these are satellites that are more massive than you or I listening, but they're still small by satellite standards, where, you know, often our planetary missions, you know, Perseverance, amazing rover, it's going to land a 1-ton spacecraft on Mars. So by comparison, you know, 500 kilograms is small. One of the aspects, though, is that, you know, we do not yet have good scientific instruments for doing science in a 10 by 10 by 10 centimeter cube, but we have great instruments for doing science from something that's, you know, the size of the desk or the table that you're probably sitting at or couch that you're sitting on while listening to this talk. So if we go to the next slide, as I mentioned, we're in a kind of a revolution for Earth and beyond. You may have heard of Planet Labs or Black Sky. They're looking to return real-time imagery from most places on Earth with a fleet of satellites like what you see on the shelf there. Or you may have heard of Starlink and SpaceX, who are doing internet telecom from space. And then, of course, we're in the starting generations of planetary science missions beyond Earth, beyond the protection of our magnetosphere, beyond our GPS for localization. We're starting to take these small satellites beyond. And so if we go to the next slide, what this is really, now we have a fleet of small satellites, in fact, that NASA is supporting. And these include planetary and solar destinations. You can see most small satellites are around Earth and the sun, but I'm pointing with an arrow to our own Lunar Trailblazer satellite, which is mated on the fleet chart because we're in development to go to the moon. And so that's the story I'm going to talk to next. And if we go to the next slide, so circa summer of 2018, early summer, so this started actually in April, May of 2018, the call came out. NASA said, we want your best ideas for ride-along missions that you can only spend $55 million on, you know, by comparison, the Perseverance rover is something like $2 billion. So 55 million, $2 billion. Okay, so ride-along missions, 55 million. The maximum you can be is this Espa Grande size, which is about 300 kilograms. And we're seeking, though, the best science, the National Academy certified decadal science. And so you, me, our team as scientists had to be really creative, because you have to think about, okay, what is the best science per dollar, right, that you can accomplish in these constraints that are fairly constrained, but you're taking advantage and riding the wave of this whole new industry. So there are a few topics, especially in the inner solar system, near to Earth, where you don't need such a crazy propulsion system or a crazy communication system for your satellite. There are some big science questions that are amenable and accessible to investigation by small spacecraft, and water on the moon is one of these topics. And so if we go to the next slide, this is where Caltech is a unique environment. And in fact, KISS, our Keck Institute for Space Studies that's sponsoring the lecture, actually played a huge role in Lunar Trailblazer, because it got me, a scientist who mostly studied Mars, and occasionally dabbled in like ice on, you know, things like Europa and Enceladus. It got me engaged in the science of the moon with a workshop that was sponsored by Caltech-connected folks, alumni, professors, postdocs, Paul Hain, Dave Page, Andy Ingersoll. So I owe a huge debt of thanks to them for organizing this amazing Keck Institute for Space Studies workshop called New Approaches to Lunar Ice Detection and Mapping. And indeed, one of the recommendations was a mission very much like, even called, although that was actually unintentional, but even called Lunar Trailblazer. That is a nanosat should be developed and launched to investigate lunar volatiles. So if we continue forward, then this is the Lunar Trailblazer mission. Lunar Trailblazer was selected in June of 2019. We put the proposal together, submitted it, crossed our fingers, and we're fortunate enough to be one of 3 selections as part of this simplex call for ride-along ESPA or ESPA Grande size satellites. And we are a simplex mission to the moon. We were confirmed as not being in competition, but rather like any normal mission, we have to just pass our review in September 2019, because NASA managed to find enough money for all 3 to go forward in this grand experiment of planetary science from small satellites. And then we were confirmed to get a ride to the moon on the IMAP heliophysics mission, which is heading somewhere else entirely to an L1 point, a point of gravitational stability between the Earth and Sun to monitor the Sun. But it has extra launch mass, so it's going to be carrying 4 satellites along the way, and that is going to be Lunar Trailblazer's ride to space. So if we keep going, one of our mission objectives are very much like what I was telling you about. I don't want to dwell too much on a text slide, but our goal is to understand the form. So what type of water is it? OH, H2O, that ice, or those little hopping water molecules. So what is the form, the distribution? So let's make a map of water on the moon, and how does water cycle on the moon? So form, abundance, distribution, we want to understand that as a function of latitude as you go toward the north and the south poles, as a function of the age of the soil, and as a function of the rock type. We also want to measure whether water is time variable, and we want to determine which permanently shadowed regions have ice, how much is there, and get the best map of those for the future, and understand how temperature influences the form and abundance of water that we see. And along the way, we get some cool bonus science. For those of you who are geologists, we'll get the best compositional maps as well of different rock types, silicic rocks, plagioclase-rich rocks, olivine-rich rocks, basalts. So it'll be very exciting, and we'll be paving the way for reconnaissance and landed missions. If we go to the next slide, and you might have to go ahead to the slide that's entitled Lunar Trailblazer Team and Organization. I just want to give you to the slide Team and Organization. I'll just give you a sense of all the people that are involved in this mission. And we're in the early stages. We're a year in, but there are already over 100 people involved. So everywhere that you see light blue on this slide is Caltech. So I'm the PI, and we're in charge of the contract to make the spacecraft. Our partner on this is JPL. Caltech manages JPL, which is the NASA Center, Federally Funded Research and Development Center. So JPL is our partner, and JPL has the overall management of the mission, including our project systems engineer, who coordinates all of the engineering pieces. I'm a scientist, not an engineer, so I am privileged to work with the JPL team to coordinate our engineering pieces to build our spacecraft. And Sam Eastlass is our mission assurance to make sure that we are meeting all of the standards to be successful. Our spacecraft is going to be built by Lockheed Martin in Denver, Colorado. And we have 2 instruments, one from JPL, an imaging spectrometer that I'll talk about shortly, and another from Oxford, a lunar thermal mapper camera, the University of Oxford in the UK. So we have some international participation. I think what's an exciting part for Caltech is the piece that you see hanging off on the right, the mission systems, because we will be operating Lunar Trailblazer from the IPAC, the Astronomy Center on the Caltech campus. And this is very exciting because one of the things that I want to do with Lunar Trailblazer is not only blaze a trail of small satellites to the moon, find water for future exploration and to support humans, but also to really kind of be trailblazing in terms of involving students in early stages of mission operations. I got involved in this by working the Mars rovers when I was still an undergraduate student, and I want to pass that on to Caltech students and also, you know, our partners just across the corner at PCC, who also are a wealth of talent for getting involved early in missions. And so if we just go to the next slide, we have NASA, when we proposed something called a student collaboration option, which NASA could choose to fund or not as a plus up to the mission. So our student collaboration option is underway even in this design phase, led by Jasper Myra, who's a gap year student who's come to Caltech after his undergrad. And we have one intern from Caltech working on mapping existing water ice databases on the moon, and 4 from PCC who have been helping with science communication, web, and GIS. So it's been super exciting to engage the students in this journey of exploration. If we keep on going, and we can skip ahead to the slide entitled University-Based Operations. As I mentioned, I don't want to belabor this, but one of the things what we'll be doing is we'll be communicating through the Deep Space Network from Caltech, using the resources here to route our commands from a Caltech Ops Center for Lunar Trailblazer through the Deep Space Network, the set of dishes in 3 places around the world, to the moon, to Lunar Trailblazer at the moon, and then getting that data back again where it hits the ground at Caltech, where we evaluate the safety and the scientific performance. So it's going to be a really exciting set of operations that we're going to be hosting here on campus. So let's keep going forward. And one of the things that Lunar Trailblazer is doing is acquiring, it's a spacecraft that's basically, once we launch, we get to the moon in approximately 6 weeks after launching. We kind of go out with the IMAP heliophysics mission toward L1 and then kind of do a U once we're released and spiral back down to the moon, capture in the lunar orbit. And then from a 100-kilometer mapping orbit over the surface, we're push brooming. So imagine that you're sweeping a broom across the lunar surface, and we're kind of looking a little bit to either side, acquiring targets as our spacecraft moves along. On the next slide, you'll see that we carry 2 instruments. We're going to go into a little tech speak for a moment. We have 2 capable high heritage instruments. The HVM cubed instrument, the high resolution volatiles and minerals moon mapper, its name is intentionally following M cubed, which first found water on the moon. It's a very similar design, but it has some important innovations that allow us to be much more sensitive to water and also critically distinguish ice from H2O molecules hopping around from, OH attached to minerals, to learn what is the water on the moon. So that's HVM cubed that will have also a 3 or 4 times better spatial resolution on the surface. The second instrument, Lunar Thermal Mapper, is focused on primarily mapping temperature through 4 channels in the long wavelength infrared using thermally emitted light from the surface. But we'll also have many channels to get good compositional data to map silicates on the surface better than we've been able to do before. If we go to the next slide, a critical piece of the approach, which I'll talk about a little more in a sec, but is that these instruments are co-nested. So they, as the spacecraft sweeps along the surface, the data they collect is collected at basically the exact same time and in the same location, so that for every image that we have on the moon that shows where the water is and what its form is via the spectra, so HVM cubed collects an image, but for every pixel in the image, there's an associated spectrum. That's the rainbow that you kind of behind the image that you see on the slide. For every pixel, there's a spectrum. Those spectrum have fingerprints like what's on the right-hand side, where you can tell the form of water because we have a much expanded higher resolution wavelength range. And then what you also get is in that yellow strip, we have temperature for every single one of those pixels, in fact, at even higher resolution in the water. So we know exactly what temperature it is, and we know what the water is doing. And that's really important because those are the biggest outstanding questions, the form of water and its temperature. If we go to the next slide, I'll delve a little bit deeply into the science for the next 3 slides to finish, to finish off here. So MCube discovered water on the moon, but it was not really optimized to characterize it or even know how much was there. So we're going to answer with Lunar Trailblazer the questions: are certain rocks and soils enriched in water? If so, why? What is the form of the water? Molecules hopping around or big blocks of H2O ice? And it's probably different at different places on the moon. And third, does that water vary with time? If so, how? The data that I'm showing on the right here highlight that we have a problem right now because we see that dip to the water, but how much it dips depends on the temperature. And if we go to the next slide, there's a little animation that kind of makes this point of why the MCube data leave us with some open questions. So if we just click so that animates, what you're seeing in green is the water absorption. And the spectrum is coming up as it gets warmer. Okay, so we'll show this again shortly once you've had a first look at it. But what's basically happening is, some of you might recall from physics class, that with black body radiation, as your temperature gets warmer, you're emitting more radiation. And then that radiation is also moving to shorter wavelengths. So what happens as the moon gets warmer is that critical absorption at 3 micrometers that tells you about water, as the temperature increases, it starts to go away and it starts to change in its shape. So what we are doing with Lunar Trailblazer is we are using 2 instruments. We're using the LTM instrument to get the temperature, and that allows us to independently correct the data at the shorter wavelengths, so we can really get at that water absorption without the ambiguity of how deep it is because of this temperature issue of the thermal emission intruding into the water signature. So if we continue, and I will say that this graphic was put together courtesy of one of our interns. And so if we continue onward, let's go forward to the next slide, which is entitled How Trailblazer Advances the State of the Art for PSRs. How Trailblazer advances the state of the art for PSRs, these permanently shadowed regions. So let's see, I'll pause because maybe I'm lagging. I'm not sure if we're on the PSRs slide. The slide should be entitled How Lunar Trailblazer Advances the State of the Art, 2 of 2 PSRs. I'm going to keep talking, assuming that we're there. So the second part is that MCube saw hints of water ice in certain permanently shadowed regions, and it saw this with using the spectroscopic features of water ice at shorter wavelengths, actually. So these are weaker absorptions. So a few craters, when you average like every single pass and you integrate over a lot of pixels, you can see that a few of these craters actually host water ice, which means that it's sitting there right on the surface available for us to map. But MCubed was not sensitive enough for us to actually make a map. So, you know, you could kind of tell that there was something there on like a 5 by 5 kilometer, but if you like wanted to land a rover or land an astronaut, you'd be hard pressed to point to like where on the lunar surface is this water. So one of the things that Lunar Trailblazer is going to do is it has enough sensitivity to map in these permanently shadowed regions to actually make a map of where the water is and where the water isn't, which is very important for future landed missions, whether robotic or human. And the other thing is that we'll be able to see whether there's anything else there. Are there organic molecules that were, you know, delivered from comets or other? What else is there? Is there anything there in addition to water in those shadows? And if we go to the next slide, and this is we're hitting the end here. If we go to the next slide, this is our most sensitive measurement, because what we have to do is remember these are permanently shadowed regions. This measurement relies on reflected light coming from the sun, being absorbed by the water, and then coming back with this signature. But these areas are not getting direct sunlight. So you might say, how are you going to make this measurement at all? Well, the answer is that these areas are getting indirect sunlight. And you can see it in this artist, again, a product of our student collaboration. Science needs art. And so what you can see here is that there's light that's actually shadowed that's scattered into those shadowed regions by light bouncing off a crater wall, then into that shadowed region. So you can just make out the faint outline of water. And we need a 1 part in 10,000 performance of our instrument to be able to sense that, and that is what we will achieve. And so this is the trickiest measurement, but also the most rewarding part of Lunar Trailblazer science. So if we continue onward, why is this important? Well, the big picture is the next generation of lunar science wants to figure out what is this water, how old is it, what is it made of, how does it get there? But the next generation of our human lunar exploration will be fueled by water. And in fact, the resources for oxygen, for perhaps the greenhouses that are showed in this artistic impression, but also for fuel as you split hydrogen and oxygen off to make resources. So resources are also a key portion of this, and Lunar Trailblazer will be providing the best maps of water on the moon. So if we continue onward here in terms of our timeline, so our timeline here has a bunch of NASA speak. Phase AB is the design phase, and that is where we are now. So we proposed in July of 2018. We were selected in June of 2019. We got news of what our ride would be in December of 2019, and we're in the middle of this phase AB, which is the design phase. We don't just go out and buy a bunch of components. We think about what we're doing first. So we're in the middle of that design phase now and going through the set of NASA reviews, culminating this October in a preliminary design review, after which NASA will give us the go-ahead to proceed forward to final design, build, and implementation, which are in phases C through D. IMAP doesn't launch for a bit, so we'll be entering into a storage period after we finish, but then we will soon be onward to the moon 2024, and with the possibility of potentially going earlier, but we're excited to have our IMAP ride. So if we finish off here on the final slide, just to remind you what you're doing, tell you where you can go for more resources. So it's very exciting, and I'm privileged to be telling you about this Caltech-led mission to the moon that stemmed out of a KISS workshop and involves this exciting small satellites, and it will involve our students in exploration. We're going to answer a number of the most important science questions about water on the moon, as well as pave the way for future and human and robotic exploration of these deposits. So we're at the start of an exciting journey. I encourage you, if you want to learn more, check out trailblazer.caltech.edu. Follow us on Twitter, and I'm happy to take any questions. Thank you.
Great, thanks so much, Bethany. That was a great talk. It looks like we should have time for a few questions here. So the first question from the audience is, Lunar Trailblazer is just the latest missions to help us answer questions about the moon. Earlier, you mentioned the moon didn't have craters, but also volcanoes and volcanic deposits. For some of us who might not be familiar, can you give us a, oh, sorry, I misread that. So earlier you mentioned the moon didn't just have craters, but also volcanoes and volcanic deposits. For some of us who might not be familiar, can you give us a brief overview of the moon's geologic history and how water might have gotten there in the first place? And are the volcanoes still active?
Okay, yeah, and I only briefly touched on the how water could get there slide. That was on the graphic that had the lunar water cycle, and I said artists needed to draw the lunar water cycle. Basically, there are at least 3 sources of lunar water, and now again, it depends what I mean by water. So do I mean OH, do I mean H2O hopping around, or do I mean water ice? Okay, so here are the possibilities. 1, so we think that some of the water in rocks is from volcanic activity. And without going into too much detail, something that happens in volcanic activity is that when magmas erupt onto the surface, if you only partially melt the rocks, you tend to get elements and materials in those magmas that are incompatible, that don't like to be in rock. They go into the melt first. And this includes, magmas that are rich in silica. It includes some things like bigger ions like potassium, and it actually also includes compounds like water. So in certain types and styles of volcanic eruptions, you can get water concentrated in the magma. This is what creates very explosive volcanic eruptions on Earth, are gases and water in the magma. So one thing I mentioned was pyroclastic deposits. These are explosive volcanic deposits on the moon, and they, in some cases, have an enriched signature of water, but not all cases. So if you're a geologist, this is very interesting. You want to figure out why this is and what it's telling you about the processes in the interior in the moon that are contributing to rocks. So that's what the water in rocks, that's maybe a part of the story of water in rocks. The other source of water is impacts. So what do I mean by that? So comets are balls of mostly ice with sometimes a little bit of rocky bits. So comets of all sizes have impacted the moon throughout its history. Asteroids, some asteroids are stony, some are metal, some are icy. So asteroids hitting the moon, and then, you know, little micro asteroids, they're called interplanetary dust particles, also sometimes have H2O. So over its entire 4 billion year history, the moon has had this infall from comets, asteroids, and then these little IDPs, these little interplanetary micrometeorites coming in. Some of these, many of these, are delivering some fraction of water. A key question that we do not know the answer to is how old is the water on the moon? That's one of the things that if we send a landed mission to ever investigate these ice deposits, or if we collect samples that have a lot of OH or H2O on them, we might be able to figure it out by looking at the isotopic signatures of the water and trying to trace sources. Maybe some of the water has layers of water and rock. So we can try to figure out the answer to these questions, but first we have to find the water. In order to ask these questions in big water ice deposits, we have to first make the map to know where it is, which is part of Lunar Trailblazer. So those are the two pretty biggest sources of water on the moon.
Great, thank you. Yeah, hopefully we get there one day. So we'll go on to the next question, which is small satellites seem to be fascinating and promising new way of doing science, but I imagine they also represent some unique challenges. What are some differences between how you and Lunar Trailblazer have approached collecting valuable science compared with, say, a bigger mission like a Mars orbiter?
Yeah, that's a great question. So small satellites work in part because they are less expensive and smaller, and so you can then get these less expensive ride-along slots on rockets. Now, being both having less money in your budget and less mass to play with when you're trying to put together your components are two big challenges. And so in terms of the money side of things, which always matters in exploring space, one of the things that we're able to do is rather than some of the larger missions that use custom parts, in large part, small satellites are now using commercial off-the-shelf components that are not very different from what a hobbyist could get. They're sort of one grade up in terms of maybe 2 grades up. So they're space hardened, but they're not necessarily tested to the same, you know, inch of their life as if you were going to send them all the way to Europa and the like crazy magnetic radiation belts of Europa. So there's a lot of use of commercial off-the-shelf components that are 99% reliable instead of 99.99% reliable. And believe it or not, that those extra fractions of the decimal are what are really important oftentimes in the space mission costs. The other challenge is of mass of a small satellite. And it's just because your components, you have to be very judicious and careful and thoughtful about taking the components you need and not what you don't need. And also miniaturizing, if you're moving beyond Earth, satellites in low Earth orbit can use GPS to navigate and know where they are. Just as a for example, you can't do that once you're beyond Earth. You need to use your radio for tracking, and you need to also use your radio to communicate with Earth all the way back, you know, through the big dishes of the deep space network. There's less communication infrastructure the further out you go. So the two biggest challenges from a technical perspective for small satellites right now are having the communication systems to do beyond Earth communication, and also having the propulsion systems to get there in a small enough package. it's, you know, people have been to the moon before, right? It's fairly, it's been done, but it's hard to do it in a small package. And so that's where we're kind of pushing the tech. We're pushing the tech to get better for comm. We're pushing the tech to get better for prop. And then that has feedbacks back to Earth, where it'll be better for, you know, everyone back on Earth too, in terms of comm and prop. So yeah, there's a nice synergy of technology.
Yeah, great, thank you. So our next question is, lunar science especially seems to be increasingly valuable as we look ahead to the mission planned through the Artemis program. In addition to mapping where the water is for resources, how do you hope the data collected from Lunar Trailblazer will guide future science carried out on the moon, with on being highlighted here?
Yeah, science on the moon. So one of the things, there are a few things that excite me about Lunar Trailblazer. One, I really am quite excited about the maps that we're going to produce of water and maybe other volatiles in the permanently shadowed region. I mean, I'd love for our mission to discover, you know, organics on the moon that, you know, maybe came from rocks on Earth long ago, or from, more likely, from asteroids and comets that have impacted, and this is this deep freeze repository of the delivery of carbon-bearing compounds and water-bearing compounds to Earth, which are, of course, essential ingredients for life. So the moon may be trapping at its poles this really long-term record of some of the most important elements and compounds for life delivered to Earth over time, carbon and water. So I'm very excited about what we'll do in terms of creating maps of lunar water ice. One of the things those maps will do will let us pinpoint sites for future exploration, something I didn't talk about at all today, but something else those maps will do is allow us to test theories of how the moon's orbit and how its axial tilt evolved, because where water ice is stable will effectively sort of provide the retrospective map of where the sun was not, which means which poles were in shadow and which weren't, and that lets you actually understand how much the moon has wobbled on its axis over time by figuring out what was cold for a really long time and what wasn't. So there's this cool, like, orbital geophysics that having good maps of lunar water lets us do. And then when, you know, speaking of water on the sunlit side, we'll have the best maps of where these anomalous regions of high water are. So in some cases, we'll probably be able to figure it out by looking at the rock types that are there, like which rock types is how high water associated with which soil types. So in some cases, we'll be able to definitively answer questions with Lunar Trailblazer. In other cases, we may be pinpointing places to be like, go send your lander here to do more investigation. So those are just a few of the things I hope to learn.
Yeah, cool. And I know there were several points where it seemed like you were alluding to we have to be careful about the water on the surface, and maybe we don't want to land right on top of it, but next to it. So there's a lot of considerations that I'm sure will come out of this.
Yeah, one of the aspects is, if we're looking for water, we don't want to, when we land our spacecraft, we bring all kinds of volatiles with us, you know, as the exhaust is coming off when we're landing. We don't want to contaminate what we're studying. So we have to land sufficiently far away that we don't contaminate what we want to study, but close enough that we can get there.
Yeah, it'll be a fine line to walk, I'm sure. So the next question is, are there many undergraduate and graduate students, both here at Caltech, as well as members of the public interested in being part of the Lunar Trailblazer? Oh, sorry, there are. That was not a question. There are many undergraduate and graduate students interested.
I think that's great.
Yeah. So how do people get involved and show their support?
Yeah, well, you know, follow us on Twitter, follow us on our website, stay involved with Twitter. We're doing a bunch of things because, you know, one of the things I really do feel strongly about is kind of fostering the next generation of explorers. Space missions are exciting. Many people don't realize all the pieces that go into it, but, you know, I'm showing bits of art, right, that are required to communicate our mission. So it takes artists to make a space mission. It takes engineers to make a space mission. It takes you know, experts in geographic information systems and geology, you know, so it takes all kinds of pieces. So that's why I'm really excited in Caltech and PCC to be engaging our undergraduate communities to these different roles, whether they be science or engineering or art or even business. We have to manage our $55 million budget as well, right? So there are all kinds of opportunities that are really important to support space. And frankly, they're all good jobs here on Earth. And so it's really exciting to me to, engage more people in the excitement of space exploration. So in terms of getting involved, if you're at Caltech or PCC, please reach out. If you're at one of our partner institutions, Oxford, Brown University, University of Central Florida, Northern Arizona University, or Johns Hopkins Applied Physics Lab, we've also got opportunities with our co-investigators there.
Great, thanks so much. And I just looked at the time, realized that's all the time we have today for questions. There were so many more we couldn't get to, unfortunately. So just as a little thank you for spending the time to put this really interesting talk together, we sent you a small gift, so we're hoping that you could open that for us and show everyone what you got.
It was very mysterious. Kathleen from KISS came by my house on Friday, and she's like, "This package is for Monday," and I'm like, "Okay." So, all right, this got. Oh, can you see it? No, this got dropped off. On,
yeah, I think you might have to turn your background off.
I might have to, but we'll see what we can do. All right. The big reveal. Oh! It looks like a moon. Very cool. It's like a lamp. It's the lamp of the moon. This is going to be super cool. Thank you very much, Kez. My own lunar globe. Super cool. This is great. Appreciate it. Very fun to talk to everyone. I only wish it could be in person.
Yeah. Thank you so much again, Dr. Ellman. So I wanted to just thank you, one last time. The talk was fantastic. And then also give a quick thank you to all of our guests for joining. We're up in the hundreds here, which it'd be tough to find a place on campus to fit everyone in. So, and then I also just wanted to give a quick announcement or reminder of our next KISS webinar, which will be on September 2nd. And that's regarding the robotic exploration of Titan with the Dragonfly missions mobility system. So thanks again for joining, everyone.
Right, thank you all.